Good morning, friends. In our chapter number 12, Electromagnetic Induction, we have studied a new topics, Motional Electromotive Force. Here, the first are translational motion of a conductor. Consider a rectangular frame of wire ABCD of area Lx is situated in a constant magnetic field B. It is as shown in figure. As the wire BC of length L is moved out with velocity V there, the flux phi through the frame ABCD is BLX. The magnitude of the induced EMF can be written as the flux phi is equal to BA is equal to BLX. Now the flux B through the loop, it is increasing with time. From the flux rule, mod of E is equal to d phi by dt. Now we can put the phi's value. It is equal to d in brackets of BLX upon dt. Therefore, we can get the equations BL dx upon dt is equal to BLV, where V is the velocity of the wire. BC increasing the length of X of the wire ABCD, that is AB and CD. A charge Q is carried through along the moving of wire BC. Its experience Lorentz force. It is given by F is equal to Q V multiply vector V multiply by vector B, which is perpendicular to the V and B. It is as shown in figure. Now the translation motion of conductor in method second. Consider a rectangular frame of wire ABCD of area Lx is situated in a constant magnetic field B. It is as shown in figure. As the wire BC of length L is moved out with velocity V, then the charge Q moves a distance L along the wire BC. The work done by the Lorentz force is W is equal to capital F into small l is equal to Q in brackets of vector V multiplied by vector B into L is equal to QVB sine theta into L, where theta is the angle between vector B and vector V. The EMF is generated is E, work upon charge, that is E is equal to work upon charge W upon Q. We know the value of W, that is work, is equal to QVB sine theta into L upon Q, that is charge. Therefore, we can get the equations. QQ gets cancelled. VB sine theta into L. That is For maximum induced EMF, sin theta's value, sin theta is equal to 1. Therefore, E will be sin theta into L for theta's value 90 degree. Therefore, E max is equal to BLV. Here, the equation E is equal to work upon charge, and equations E max is equal to BLV is proved that for any circuit whose part moves in fixed magnetic field, the induced EMF is the time derivative of flux phi, regardless of the shape of the circuit. In a region where the magnetic field is changing with time, electric fields are generated. Now next, motional EMF of rotating bar. Consider a small segment dr of the bar at a distance r from the pivot. It is a short length dr at the conductor which is moved with velocity v in a magnetic field B and has an induced EMF generated in each like a sliding by. It is as shown in figure. The induced EMF dE in the small segment dr of the rotating conductor is dE is equal to BV dr. Now the total induced EMF in rotating rods E is equal to integrations of dE is equal to integrations of, we can put the dE value, integrations of BV dr. Therefore we have get the equation E is equal to integrations of B WR dr. Therefore E is equal to B and W integrations of 0 to L R dr. Now E is equal to dW L square upon 2. Now the equation we have get E is equal to 1/2 BW L square. It will be compare the above result with the induced EMF is sliding with bar E is equal to BLV. Now, next topics, induced EMF in a stationary coil in a change in magnetic field. In a magnetic coil system, a permanent bar magnet is mounted on an arc of semicircle of radius 50 cm. It is denoted in figure A. The arc is a part of rigid frame of aluminum and is suspended at the center of arc so that whole system can isolate freely in its plane. A coil of about 10,000 tons of copper wire loop arc so that the bar magnet can pass through the coil freely. To measure the induced EMF, a capacitor C and diode T are connected across the coil. It is as shown in B. Thus, the magnetic field changes quite slowly with time when the magnet is far away. and changes rapidly when it is approaches the coil. The variation of magnetic field B with time, it is as shown in figure C. Now consider the effect of pulses on the charging circuit. In figure B, the diode will conduct only during positive pulses. At the first half swing, the capacitor will charge up to potential, say E1. During the next half swing, the diode will be cut off until positive pulse is produced and the capacitor will charge up to a slightly higher potential, say E2. It is as shown in figure. This will continues for a few oscillation till the capacitor charges up to its peak value E0. It is as shown in figure by the voltage per EMF pulses. At this stage, ammeter will show no kick, further increasing in the current of the circuit. The equations for induced EMF can be written as mod of E is equal to mod of d phi by dt is equal to mod of d phi by dt is equal to d phi upon d theta into d theta upon dt. It is in a mod. At theta is equal to 0, the mean position, we have maximum value of phi. Therefore, d theta upon dt can be deduced from the equation, because d phi upon dt is equal to 0 at theta is equal to 0. Therefore, we have get the equation theta is equal to theta 0 sine 2 pi Vt. Now here theta 0 is the amplitude of oscillating magnitude of magnet. Now the frequency V is equal to 1 upon time period, that is t. Therefore, theta is equal to theta 0 sine 2 pi upon t into small t. Therefore, d phi upon dt, theta 0 cos 2 pi upon capital T into small t into 2 pi upon capital T. Therefore, d theta upon dt is equal to 2 pi theta 0 upon t cos 2 pi upon t into small t. For the peak voltage EMF, that is E0 in the induced EMF pulse corresponds to d theta upon dt, that is maximum. Hence, we conclude that mod of E, that is E0 is equal to d theta upon dt is maximum. It is approximately equal to d theta upon dt max into 2 pi theta 0 upon t. For a given magnet coil system, the peak induced EMF E0 is directly proportional to the amplitude theta 0. and inversely proportional to the time period capital T.